In 1965, two mathematicians published a 4-page paper that ran a calculation 800,000 times faster than the previous method. The fast Fourier transform now runs every time your phone connects to 5G, every MRI scan, every MP3. I pulled the original paper, the IBM lab notes, and the 2021 Annals of Mathematics result. Every number in this video has a citation behind it. Siachors. This matters now because in March 2021, the Annals of Mathematics published a result that used FFTs to settle a 50-year-old conjecture about how fast computers can multiply numbers. A standard disclosure first. Some links below earn me a commission at no cost to you. It doesn't affect my recommendations. And I'm not a financial advisor. This is educational, not financial advice. Over the next 15 minutes, where the FFT came from, how the butterfly works, and why a 1964 Cold War algorithm still runs the internet. The discrete Fourier transform takes a sequence of numbers, say audio samples, and tells you which frequencies are in it. The naive way to compute it costs n-squared operations. For 1 million samples, that's a trillion operations. On a 1 microsecond per operation machine, that takes about 11.5 days, per the MathWorks technical article. Joseph Fourier formalized the underlying math in his 1822 treatise, Théorie analytique de la chaleur. But the algorithmic shortcut, the FFT, has a stranger history. Carl Friedrich Gauss wrote down a recursive version around 1805 to interpolate the orbits of the asteroids Pallas and Juno. He published it in Neo-Latin, posthumously, and never analyzed the cost. So it got rediscovered. Danielson and Lanczos worked out a partial form. I.J. Good published the prime factor algorithm in 1958. None of these caught on. The breakthrough that everyone uses came from a Kennedy Science Advisory Committee meeting in 1963 about detecting Soviet nuclear tests with seismometers ringing the USSR. That's where John Tukey of Princeton sketched the idea on a piece of paper. And that's where the story actually starts. At that 1963 meeting was Richard Garwin, head of IBM's Watson Scientific Laboratory at Columbia. Garwin recognized the algorithm had uses far beyond seismology, radar, spectroscopy, signal processing. He went back to IBM and asked research to assign a mathematical analyst. They picked James Cooley. In 1964, at IBM's Thomas J. Watson Research Center in Yorktown Heights, New York, Cooley coded the algorithm in Fortran on an IBM 7094. That was the first working demonstration. The 1965 paper reports the result plainly. A size 2048 complex DFT ran in 0.02 minutes, about 1.2 seconds. Danielson and Lanczos, working by hand, had needed 140 minutes for a size 64 transform. Rescaled by problem size, that's a speed-up factor of roughly 800,000. Against existing computer codes of the era, the FFT was about 100 times faster. The paper was 4 pages long, Mathematics of Computation, Volume 19, pages 297 to 301, April 1965. 4 pages that quietly rewrote signal processing. The FFT factors the DFT matrix into a product of sparse matrices, so most of the multiplications are zeros you don't have to do. The Radix-2 Cooley-Tukey algorithm, the simplest and most common form, works by divide and conquer. Take a sequence of length n, where n is a power of 2. Split it into the even index samples and the odd index samples. Each half is a smaller DFT of length n over 2. Recurse. Combine. The combine step is called a butterfly. A butterfly takes 2 complex numbers in, applies 1 complex multiplication by a twiddle factor, a root of unity, and produces 2 complex numbers out. 1 complex multiplication, 2 complex additions. For length n equals 2 to the m. The algorithm runs log base 2 of n stages. Each stage performs n over 2 butterflies. Total, about n over 2, times log base 2 of n complex multiplications. A real implementation uses fewer than 5 n log base 2n floating point operations. Gilbert-Strang's standard example, at n equals 1024, the naive method needs 1,048,576 multiplications. The FFT needs 5,120. Saving factor, over 200. In 2026, the FFT is running in your devices right now. When your phone connects to 4G LTE or 5G NR, it's running OFDM, orthogonal frequency division multiplexing. OFDM splits a wideband signal into many closely spaced orthogonal subcarriers, and the modulation and demodulation are literally inverse FFT and FFT. Wi-Fi works the same way. When you go through an MRI, the scanner doesn't measure pixels. It measures raw signal in what radiologists call K-space, the frequency domain. A two-dimensional inverse FFT reconstructs the anatomical image. CT and ultrasound use related transforms. JPEG image compression is built on the discrete cosine transform, a close relative of the Fourier transform, computed with FFT-style algorithms. MP3 audio compression, radar pulse processing, spectroscopy, seismology, polynomial multiplication for cryptography. In 1994, Gilbert-Strang called the FFT the most important numerical algorithm of our lifetime. In 2000, IEEE's Computing in Science and Engineering listed it among the top 10 algorithms of the 20th century. The list is short. The FFT is on it. There's a software story here, too. By the late 1990s, every CPU architecture wanted its own hand-tuned FFT. Different cache sizes, different vector units. In 1998, Matteo Frigo and Stephen G. Johnson at MIT released FFTW, the fastest Fourier transform in the West. FFTW computes DFTs of arbitrary input size in ON log n time on real and complex arrays of arbitrary dimension. Its trick is self-tuning. At runtime, it measures your hardware and assembles an optimized plan. In 1999, FFTW won the J.H. Wilkinson Prize for Numerical Software. It's licensed under the GNU GPL version 2 or later, with a commercial license available from MIT. If you've ever called the FFT function in MATLAB, you've called FFTW underneath. In March 2019, David Harvey at UNSW Sydney and Joris van der Hoeven at École Polytechnique posted a preprint. They showed that two n-bit integers can be multiplied in ON log n bit operations, using multidimensional FFTs over the complex numbers. That settled a conjecture Schoenhagen and Strassen had made in 1971. The paper appeared in Annals of Mathematics, Volume 193, Issue 2, pages 563 to 617, March 2021. The FFT isn't one algorithm, it's a family. Radix-2 Cooley-Tukey is the textbook version, requiring n to be a power of 2. There's Radix-4, Radix-8, mixed radix for composite n, and split radix, which minimizes operation counts. There's the prime factor algorithm of I.J. Good from 1958 for coprime factor sizes. There's Bluestein's algorithm and Rader's algorithm for prime length transforms. Real input variants exploit conjugate symmetry to roughly halve the work. There's a quantum version, the quantum Fourier transform, a sequence of 1 and 2 qubit gates, is effectively the Cooley-Tukey FFT realized as a particular factorization of the Fourier matrix. It's the core subroutine inside Shor's quantum factoring algorithm. All of these share the same insight Gauss had in 1805, that Tukey rediscovered in 1963, and that Cooley coded in 1964. A Fourier transform is a sparse matrix in disguise. A sparse matrix in disguise. That's the whole idea. Every time you stream music, get a chest scan, or open a web page over Wi-Fi, a 1965 algorithm is reshuffling that matrix into something a computer can finish before you notice. A few honest caveats most explainers skip. First, it is not rigorously proven that discrete Fourier transforms require omega of n log n operations, even for power of 2 sizes. No faster algorithm is known. but no matching lower bound has been established either, per the Wikipedia survey. The FFT is the fastest known method, not provably the fastest possible. Second, the Cooley-Tukey paper claimed a 0.02-minute runtime for size 2048 on the IBM 7094. The 800,000 times speed-up figure compares that to a manual Danielson-Langstos calculation at size 64. The fairer comparison, against existing computer codes of the era, is the 100 times speed-up figure cited by the IEE milestone documentation. Both numbers are real. They measure different things. Third, Gauss got there first, around 1805. He just didn't publish, didn't analyze the cost, and wrote in Neo-Latin. The credit went to Cooley and Tukey because they published a clear paper at the moment computing hardware could exploit it. Fourth, numerical precision. FFTs accumulate floating point error across log n stages. For most signal processing, the error is negligible. For very large transforms in scientific computing, it can matter, and people use higher precision or compensated summation. The recognition followed slowly. John Tukey received the U.S. National Medal of Science in 1973 and the IEE Medal of Honor in 1982, cited specifically for contributions to the spectral analysis of random processes and the fast Fourier transform algorithm. James Cooley received the IEEE Jack Kilby Signal Processing Medal in 2002 for pioneering the FFT. In 2024, the IEE History Committee presented IBM research with a milestone award commemorating the first demonstration of the FFT in 1964 at the Watson Research Center. The plaque is now on the wall in Yorktown Heights. If you want the single best piece of background reading, the original paper is short. 4 pages, freely available through the Mathematics of Computation Archive. Cooley, J.W., and Tukey, J.W., an algorithm for the machine calculation of complex Fourier series. Volume 19, pages 297 to 301, 1965. For the modern integer multiplication result, the citation is Harvey and van der Hoeven, Annals of Mathematics, Volume 193, Issue 2, March 2021. Wang Xiao, a 1964 Cold War algorithm, motivated by detecting nuclear tests, runs your phone, your music, and your medical scans 60 years later. Gauss saw it in 1805 and didn't tell anyone. Tukey sketched it in a meeting. Cooley typed it into a 7094. If this was useful, and you want the 4-page original paper plus the 2021 Annals result in one PDF, the link is in the description. Affiliate links there earn me a commission, doesn't change the price. If you want to see the same divide and conquer pattern applied somewhere else, the next video walks through how FFT-style ideas show up in credit card fraud detection. Frequency domain features in transaction streams. That one's already up.